All right, let's get started. Hello, everyone, and welcome to our session, Power Systems and EVs at 900 volts, the next bottleneck. My name is Jalen Lewis, and I am the events manager here at Peak, and I will also be your moderator today. I am joined today by Sean Walsh, the Chief of Marketing here, along with John Tomko, our Principal Product Development Leader, where they will discuss how to upgrade your system with ease. Before we get started, I have just a few housekeeping items. Questions will be answered via the Q&A chat following the session, and the webcast is being recorded. It will be made available following the session for you to rewatch or share with colleagues. This is a monthly series, so be sure to watch out for our November 18th session, Start Me Up, using Peak Nanoplex HDC capacitors for motor start applications. Without further ado, I will now pass it off to Sean Walsh to get our session started today.
All right, let's try that with the audio on this time. Thanks, Shayla. So part of what I want to do today is help set the stage for where we're seeing the market for high voltage DC inverters going. I am going to leave all the technical part to John because I don't know that much. But what I want to be able to do is help set the scale for what we're talking about here. Because sometimes I think these component level systems, people don't quite fathom just how large the market and the number of units are involved in these. So again, prognosticators across the world will have different numbers. Precedence Research says this market will reach $98 billion by 2034. And we'll talk a little bit about what that means over the next decade in terms of specifics as we go through this. But when we think about what's happening, there's a bunch of different changes that are happening in terms of regulatory processes to try and get higher efficiency out of existing grids because we can't build power plants fast enough. We can't put up enough solar farms. You take your pick. So in the US, there's a piece of legislation known as the GETS Act or the Grids Enhanced Technology Act. This is where they're talking about adding things like silicon carbide and gallium nitride solid state switches and transformers to help speed up and improve the efficiency of power distribution and power generation to reduce loss. We're seeing the same technology used in EVs, solar renewable panels, infrastructure, and fast DC charging. You take your pick. While the US is probably modifying some of its renewable policy, I should say probably definitely revising some of its renewables policy. If you look at India, EMEA, and especially China, the growth is astronomical. And as a result, one of the other changes of using these solid state technologies is you do get higher thermal demand. So that changes how you design things. And John will take you through some more details on this. But it means that the way that you look at cooling infrastructure, the way that you look at how you design things also needs to evolve as you put these things in place. And we've seen some of the capacitor film and other high temperature components start to hit some end of life. In particular, the DuPont Tension pen material. And John's going to talk a little bit about how we think we can use our products to help offset some of that and enable this move to higher voltage DC markets. All right. So as we look at some of the applications, I don't think if you're here, I don't think there's anything here that's going to surprise you. So power grid, EVs, solar renewable, all the industrial automation. As data centers starts to move to DC buses, which we're seeing more and more with the AI-based systems, that'll happen. And then the big transportation, rail, electric aircraft, all of these things are going to use more of these DC inverters. So let me just kind of give some scale here on the numbers as we look at this. So if we look at the power inverter market for solar and renewables, according to our friends at the IEA, solar energy we're going to add 600 new gigawatts of power in 2025, ramping up to 1,250 gigawatts by 2035. If you look at both central inverters and string inverters, There's approximately 10 million new inverters are going to be deployed as part of this. So we're presuming that, they're not going to upgrade the rest, just looking at the brand new side of it. On the automotive side, this year, Bloomberg estimates that there'll be 21 million new EVs shipped. 50% of those are coming from China. By 2035, they're saying, by 2030, 40 million EVs will ship. And again, share in China will probably go up to 60 million. You multiply that on an average of 1.5 inverters across whether it's one motor, two motor, four motor configurations, the average is about 1.5. You're going to end up with almost another 75 million new DC inverters. And then you throw in what's happening in semiconductors, what's happening in other environments, and you start to see how the numbers climb so dramatically in this. And the players in the market aren't going to surprise you, but they are definitely looking at ways for new solutions. And then I just want to leave you with some of the market impressions from IEA on where they see electricity going over the next couple of years. And you could almost do a straight line trend on this chart. So coal, natural gas, not going anywhere. They're going to be around for a very long time. Huge part of the market, relatively easy to deploy, well known. There's a lot of people who are speculating about nuclear with SMRs, but so far that is not going to be in the next 3 to 5 years. That's probably going to be a little bit afterwards. But what's growing? Renewables, basically wind and solar. And the numbers I've thrown out for wind obviously are a little smaller, but the number of inverters are pretty consistent. And what's even more important when you look at the total use here is where is the new power coming from? So as we look out, and you can see back in the pandemic, coal and natural gas really surged. But as we got back into, I'll say, normal world operations, and you look at the incredible scale of the solar panels that have come out of Japan, actually out of China, um, renewables are going to drive this inverter business. That is also driving EV, fast DC charging. And together, those two major applications are going to drive market demand and the need for these higher voltage inverters. So with that, I'm going to hand it off to John and let him take you through the technical side of this.
Yeah, thanks, Sean. I'll jump right into this with a quick segue. You never really know the audience of webinars, so little introduction on inverters. I apologize for the first minute here if you're intimately familiar, but I think most average people are really familiar with converters. Every time you plug in an electronic device into the wall, you're converting AC power to DC using rectification. An inverter is doing the exact opposite. We're converting a DC field into an AC waveform. And so, this can be anything from a square or sawtooth wave, or back to the typical sinusoidal pattern that we're used to for grid purposes. The most simple form of doing this is it kind of in the middle here, where you can take a DC power supply and a single switch and change the direction that the voltage and current propagate in by simply switching between these two nodes. This is probably the more simple design that existed 60 years ago. And what you're starting to see is this transition, especially with the rise in more advanced transistor technologies, to things like H-bridge topologies are now obviously the standard. And this enables a lot more application spaces, but it's also a more complex technology for all intents and purposes. And so, a really easy example of kind of how these new topologies and technologies relate to the applications and where we can go with inverters is in grid forming purposes. So, decades ago, all you would see is grid tie inverters. And so this is a device we plug into the grid and it operates in a grid following fashion. So you have some waveform and voltage existing on the grid already, and you use a phase lock loop to synchronize to that voltage and frequency, and that's how you drive your inverter. The problem with this, though, is that this means your inverter is completely reliant on the grid being stable in voltage and stable in frequency at all times. And so this really means you can't operate in an isolated fashion or island system. And if the grid has any interruptions whatsoever, your inverter goes down. And so what these topologies start to do is let you do things like grid forming inverters. And so in this case, the inverter is completely self-reliant and uses an internal control system to produce a stable output. And so what this actually enables is solar cells to act in complete isolation. You can work off the grid entirely. But what you can also do is actually black start if the grid goes down for whatever reason. And so not only are you seeing this technology become more widespread, but we're also seeing just the general transition from kind of these typical central high inertia systems in the grid to this more distributed inverter-based network. And so, in addition to grid, the topology and inverter designs we're starting to see pop up. Going back to EV here, if you're familiar with electrical engineering, four-quadrant design. So on the top right and bottom left is that simple switch scenario where voltage and current both go in the same direction in all cases. So if I'm driving an EV, this means I can drive forward and I can drive backwards. What you've seen with hybrids over the last couple of decades is now we can start doing things like regenerative braking. And so this is actually enabled by capacitive elements within the inverter. And so now what you can do is actually drive your current and voltage in opposite directions and actually store charge. And again, this is completely enabled by changes and improvements in both the hardware and the topologies that we're seeing in inverters. And not only are these capacitive elements enabling kind of just general storage and absorption of energy for the case of regenerative braking, for example, but they also can change the net reactance of the circuit. And so what this means is you can actually change the transmission capacity of the inverter itself. And so by kind of controlling all of these elements simultaneously, what we've seen is this general net improvement in the total efficiency that you have in your inverter. And so simple example shown on the right here, you can see every couple of decades, you get a few percent improvement in the net efficiency. More so, you actually get a huge improvement on the low side of your apparent power, which is where most of your energy is lost. And so, I know when you zoom in there, you're looking at a few percent efficiency in a single inverter, but it's important to remember that, inverters nowadays are handling many multiples of gigawatts of power distribution. So 2% easily correlates to tens of megawatts of power being lost and dissipated into these inverters. And since this is in the form of heat, we'll talk a lot about this later, the low efficiency actually means you get premature system failure. And so it's more than just lost energy, it's premature failure of your system. And, I showed that plot on the right. We pulled it from a publication. Admittedly, it's a little bit of modeling, but, this efficiency trend you're seeing in the previous slide really isn't just scientific publication anymore. It's actually moving into the real world. And so conveniently, California Energy Commission actually publishes this really nice list of the specifications and weighted efficiencies of thousands of inverters that are sold in California. These are mostly for solar purposes, but it kind of applies to any case you'd have an inverter with. This list is particularly convenient because it actually uses a reference standard developed by Sandia National Labs. And so it gives you this nice apples to apples comparison of really how good your technology is in an application space. I encourage you to pull this link up yourself if you get some time. I'm only showing 10 on the right here, and they're all 99% efficiency. It goes that at 99% for quite a while. It's not just the top 10 anymore. Almost everyone's over 98%. And so this looks great. Everything's good, 99% improvement. You can do regenerative braking, XYZ. We've seen a ton of improvements in a very short period of time, but we're not having a webinar to tell you how great inverters are. We're trying to tell you where some of the problems still remain. So where are the downsides of inverters? Where can we continue improving? And it really turns out that these high efficiencies and standardized tests are great, but what we're still seeing is actually a lot of inefficiency when deployed in the field. And so a really strong example of this is shown on the slide here, where there was a massive survey of solar cells, specifically from SunEdison, and they looked at over 350 panels over a 2-year period. And so it's a nice summary data sheet of kind of how a net array of panels exist over a long duration period. And what they find is that almost 36% of energy loss in a solar system is due to the inverter itself. And so, this isn't just the 2% loss we saw on the prior slides. It's obviously a much bigger number than that when you start adding things up. But there's a bigger problem than just lost efficiency that's highlighted in this plot, and that's the dark blue bar. So if you look at the bottom there, you can actually see that 45% of tickets, so how many maintenance requests the solar company's putting in, are associated with the inverter itself. And so almost 50% of the time you have a problem with a solar cell, it comes down to the inverter. And again, this is only over the first 2 years of operation of the solar cells. The problem exacerbates itself as time goes on. And so these tickets are kind of highlighting there's a bigger problem than lost efficiency happening in inverters. Again, really strong example, National Renewable Energy Lab held a workshop last year. Again, mostly for solar applications, but most of the takeaways kind of apply to any inverter. Again, encourage you to read through the proceedings. However, kind of one key takeaway that was really interesting to me, at least, was that an insurance group reviewed 500 different photovoltaic systems across the US. And so this comprises about 11 gigawatts of power capacity. So, very large statistical analysis. And what they found was that the mean time from installation of inverter or solar cell to the time a submitted insurance claim happened was 2 years or less. And so again, even though these inverters are using state-of-the-art technologies and topologies and whatever else, there remains this constant issue of lack of reliability, particularly for these utility-based systems where we're really expecting 15 to 20-year lifetimes, which is usually the standard for grid, but instead we're seeing almost a 10x reduction across the board. And so if you kind of looked at those images that I highlighted on that slide there, one thing that's kind of really a key point in this workshop is that the failures and inefficiencies we see are really dominated by kind of one single root cause. And there's other factors. I'm like, making it singular is a little extreme, but the dominant root cause is that they're thermally induced failures. So in the previous slide, we had capacitors bulging, they're exploding. You have the PCB melting through in certain cases. And this is all due to very high internal temperature rises within the inverter. And so it's kind of important to recognize that this type of thermal failure isn't instantaneous or even observable on short timescale testing. Obviously, sometimes it is, but even small temperature rises, 5, 10 C, start to wear out devices over time. And so a good example of this is what you start to see, for example, is basically degradation of the electrical resistance of components. So as they heat up and cool down multiple times and they're cycled, you tend to see the resistance of every wire in the circuit slowly increases, particularly on PCBs. Well, if the resistance is going up, so is your ohmic heating. And so this kind of creates a feedback loop that where basically as you put more power in, you get higher temperature rises over time, which causes more resistance. And again, this just kind of propagates into this negative feedback loop. And so this is particularly relevant for kind of the transistors and capacitors that are used in inverters, where you see that the temperature ratings are usually limited by these two devices. And in our heads, we're running these only at 10 C temperature rises, so what's the big deal? But we're not accounting for kind of these runaway effects that happen. On top of that, when you think of high temperature, it's really kind of a combination of multiple factors, over voltage conditions, high current usage, normal aging. They all contribute to what we think of as kind of these high stress conditions. They're all related to this thermal induced failure that happens over time. And so one thing that kind of popped up in a lot of these DOE reports is that even though failure through thermal induced degradation is one of the dominant mechanisms of inverter lack of reliability, they actually don't recognize it as the need for the highest improvement. And so again, in another DOE workshop focused only on inverters, they actually decided that capacitors were the area that needed the biggest improvement. And so if you read through this, you'll find that it's due to an array of complex factors that lead back to the thermal failure mechanism. And so in a lot of cases, inverters are using these electrolytic capacitors where failure is kind of sudden and unexpected. And this causes a loss of stability in normal operation. And so this starts to generate even higher temperature rises, causing faster failure, and again, going back into this negative feedback loop. When using film capacitors even, in these devices, so people smart enough to move away from electrolytics, you start to see that these fatigue, again, under strenuous high stress conditions, or kind of any operation outside of the design specifications, like over voltages or high ripple currents. And this all causes the same effect, slow degradation of the capacitor that ultimately can lead to catastrophic failure of your transistor or switches within the device. And so, in other words, because the capacitor kind of acts as your stabilizer for the circuit, capacitor degradation is really a leading cause of inverter issues. And so, why is this still happening? You know, how are capacitors still being the limiting effect here? At least for me in my head, capacitors have been around much longer than solid state switches. You would have expected those to be probably the more dominant mechanism. And one major issue that needs to be called out is that people are still choosing to use electrolytic capacitors just because they're low cost with high capacitance density. And so most of the time you buy these, they have a great data sheet out of the box, but you're not really accounting for the operational lifetime. And again, these kind of high stress conditions that most inverters are exposed to. And so using electrolytics kind of as the platform here, it's very well accepted that the lifetime of a capacitor halves every 10 degrees extra temperature that it faces. But critically, particularly from a design perspective of an inverter, it's important to remember that the rating isn't actually ambient temperature that you care about, but instead the internal temperature of the capacitor that happens due to internal heat generation as you're passing current through the device itself. And so, using a quick back of the envelope calculation on the right-hand side here, you can see a capacitor that's rated with a 10-year lifetime, which is pretty standard for electrolytics, would actually be reduced to only a 2-year operational lifetime if you had an RMS current of 5 amps, just from this internal heating. Even if you had the best cooling in the world, you'll still have some degree of this internal heating you have to handle. And so while this looks really good on a data sheet, you start to see it fatigue very quickly in real world conditions. Just for fun, I added the calculation. If you double the current to 10 amps, you'll get about 5 days use out of it. And so not very effective for a solar cell. And so, what you're starting to kind of see is this transition to film-based capacitors. I'll be the first to recognize, up front, you're going to see a higher cost. As you switch from electrolytic to film capacitors, capacitors cost more, and they look like they have lower storage density. Just using the two kind of ballpark figures there, 3 microfarads per cubic centimeter for an electrolytic, about half that for a film capacitor. And so, if you kind of do some calculations around how this comes up in your design space, I put an example of this on the bottom right. It's important to remember this is for a single capacitor. You need to account for the entire system itself. And so, although the electrolytic has a higher storage density, when you compare electrolytics to film, electrolytics typically can't handle high voltages. So back to the whole point of this webinar, 900 volt systems. I'm not even there yet. I'm only at 700 volts in this calculation. And what you see is you actually need 2 electrolytic capacitors because they can't handle the 700 volts. They're only rated to 400 each. Because of this, I actually need higher capacitance of each element. So this means when I start looking at the capacitor I need for this very small 10 horsepower motor, I can actually get away with a very small film-based capacitor solely because it has the higher voltage rating. And so, using electrolytics to film one-to-one isn't always kind of the right approach. You really need to account for the whole system design. And there's a whole number of factors here that really should be accounted for. With this being said, even when we move to film capacitors and this transition that's starting to pop up, not all film capacitors are exactly the same. If you've worked with these before, you'll see a whole array of data sheets across the board. And one thing to note is film capacitors don't solve the issue of exponential degradation with temperature. Every capacitor made will exponentially degrade as you heat it up. However, what you can start to do is actually change the properties of the film within the capacitor to increase the maximum lifetime. You can't do this in electrolytics because you're always locked into an electrolytic solution that will evaporate at fairly moderate temperatures. In contrast, if you could switch to a film with a very high maximum operating temperature, in this case, I'm showing Peak Nano's LDF film, this can actually extend the lifetime compared to pre-existing film capacitors by over 2 orders of magnitude. And so if you look at the red circles I have on the right, I put a fairly small temperature rise on the capacitor. A standard off-the-shelf polypropylene capacitor might last for 10 years, which seems good enough, again, if you're not stressing it. Peak Nano's LDF would actually extend that to 1,100 years. That's probably longer than any of us care about. But what it does mean is I have a lot more tolerance for higher stress conditions. I can tolerate this internal heat generation, and now under these extreme conditions, pull more lifetime out of my system. And so kind of lumping this all together, we're seeing this transition from low voltage or moderate voltages, inverters to these high voltage 900 volt designs. And so a great example of this and kind of the imperative need to switch in our inverter designs is that pre-existing film capacitors based on polypropylene or PEN really worked well in. I lost the slides there, Jalen. Sorry. I'm just going to continue ranting and you can all listen to me without the slide here. PEN and polypropylene work fairly well under these kind of moderate voltage conditions, but the film, the base material used just isn't designed with these high stress conditions in mind. And so going back to temperature, voltage is effectively proportional to temperature for all use cases. And so what you start to see, you put higher stress on the material, and polypropylene and PEN just can't handle it. You need much thicker films. In contrast, what this kind of means is that it's almost required that you have a higher temperature film within your capacitor. And so if you could develop a high temperature version of PEN or BOPP, or in the case of Peak Nano's LDF, which is intrinsically high temperature, you can now start to tolerate these for the same thickness of film. Sorry, I'm trying to figure out how to pull up slides here. I guess with all this being said, I think that the technical aspects that really, oh, amazing. Thank you, Jalen. So going back to the slide, exactly what I just said. Higher voltage means you're putting more power through the device, which means you have higher stress. And so you need these long lifetimes. And so if you really start to dig into much more detail on kind of the technical aspects that drive films that are chosen for film capacitors, it's a lot more than just saying it lasts longer. In fact, this is really enabled by things, again, like that equivalent series resistance, how much ohmic heating you generate in your device. In the case of Nanoplex LDF by Peak Nano, you actually see that this parameter is constant as a function of temperature. Whereas if you look at almost any other material system, weirdly not even film, just any material system in the world, as it heats up, you tend to see that the electrical resistance of the material starts to increase. You go back to this idea of thermal runaway. If heat causes more resistance, it'll lead to more ohmic heating at the higher temperature, and you again propagate this thermal runaway effect. And so by having this high temperature capability where the properties remain flat as a function of temperature, you're able to actually avoid these degradation mechanisms that really kind of kill other film options that exist. And so kind of unsurprisingly, this just doesn't exist in PEN or BOPP-based capacitors because the material system can't handle it. And then if I look at this kind of from a design perspective, this really means that if high stress conditions aren't required, engineers can start to actually reduce the amount of cooling in the inverter. So far I've really been talking about stress. Let's say we're in normal, really safe operating conditions. What I can actually do is design a system using a high temperature compatible material that can tolerate the high heat generation and eliminate the need for active cooling. And so what this starts to do is give me a parameter I can play with in the design space where if I need a smaller inverter, I can actually get away with it simply because LDF enables that high temperature operation and doesn't require the same extent of cooling. And, again, never know who's on these calls. I think that's from an engineer's perspective. What I will throw in is from a procurement office perspective, engineers always want the newest, greatest toy. Cost is always very important. And usually higher performance means higher cost. But because LDF is actually based on the same type of manufacturing process that you use for BOPP and PEN, we're actually able to keep the cost comparable to BOPP, meaning it's actually a very cost-effective solution, even if you didn't need the performance upgrade. But again, it gives you that design space to kind of work in and play around with your other parameters. And so with all this being said, kind of like the high level summary here is that inverters as a whole are still completely bottlenecked by low reliability components. Even with these high efficiencies we're seeing transistor failures fairly consistently at this point, particularly in the 900-volt range due to all the high stress, high temperature cycling we talked about. And the fact that capacitors start to degrade under fairly moderate conditions actually means you're overly stressing your transistor over time. As the capacitor degrades out, you're just putting more stress on every other component. And so again, this just becomes exacerbated at higher voltage conditions. Everything I suggested about moving away from electrolytic to film capacitors, it really starts to pay for itself, not even just in kind of that nice 10 horsepower motor example I used, where under these high voltage conditions, I just need more electrolytics. Whereas the film, I can actually get to a smaller footprint. But on top of that, when you start thinking about lifetime considerations, if I have to replace the components every 2 years, that really starts to add up. And so having these long lifetime components like LDF-based capacitors actually just gives you more overhead in terms of your cost competitiveness. And then again, this all kind of ties in. If you can get to higher temperature ratings, and this isn't even true for film, it's particularly true for film, but it's really true for every component. The higher temperature rating every component can be in there means that it will have a higher lifetime and has much more current handling capabilities than something else. And so while BOPP is really challenged to support 900 volts, things like LDF start to move that forward for film capacitors in particular. That's it for me. Sorry for the little technical hiccup there. I tried to keep it going, but yeah, thank you all very much for listening.
No, you did great. Thank you both. And as we are opening up our Q&A portion, we ask that you please interact with our survey. It should just take a couple moments, and then we will jump into all of our questions and answers. So our first question is going to be, what cooling infrastructure is used today that can be removed?
So when we look at a lot of the designs that we've seen, especially in EVs, or some of the other industrial applications, they're using water-cooled based systems. They're using fans, they're using heat sinks. And three things occur. One is you have the incremental BOM cost of that. Second is you have the incremental space used and the infrastructure materials that have to be added to it. And then the third is you're increasing the service parts required in order to do this and the complexity of the systems. So we've seen a number of vendors that we've talked to come to us and say, look, we want to do this in addition to the operational performance gains, but to do it so we have a much smaller form factor and BOM cost. And in the case of many of the EVs, every kilogram that they can reduce in weight increases the range and efficiency of the battery systems that they have. So that's sort of a long way around to all the different pieces. John, you may have other thoughts on that.
No, I think that's spot on. It goes back to, I think it's a little dependent on the exact application space you're looking at. But in most cases that pre-exist right now, again, if you could just switch to higher temperature components, you completely eliminate the need for cooling. In the 900-volt case, you're never going to get away from active cooling, but you can certainly reduce the footprint of it. And so I think that's really kind of the key takeaway there.
All right, great. Our next question comes from Benjamin. Could you please shortly elaborate on the applicability of multi-level inverters, MLIs, with a higher number of DC links that split up the input voltage in contrast to one level or two level MLIs for high voltage applications?
Yeah, that's a really good question, Benjamin. I think the really high level takeaway from that is you lower the voltage stress of pretty much every DC link. Every component is just lessened in how much stress it has to tolerate. The trade-off with this is just more infrastructure. You're paying more for component cost because you need more components. You need more DC links. And so I think it's really application specific. I'm not familiar with exactly what you're working on right now, but in certain cases, it actually weirdly makes more sense to put in a higher rated system and just operate everything at the higher voltage, in contrast to kind of dividing it out through those multi-level infrastructures. And so, yeah, kind of a nuanced question, but I hope that gives at least a little bit of insight.
Next question, we have a few questions from Maria. Have you made a comparison with EPN film?
In what regard would be my first question there. But yeah, we do a lot of internal testing at Peak Nano in particular. I'm assuming this is in reference to LDF. We do comparisons to primarily BOPP, just because that's really the standard right now. But LDF actually acts kind of as a nice plug-in replacement for EPN applications. They're really kind of one for one in many senses. Oh, I see your question there, Maria. In terms of long duration tests, yeah, we do comparisons with it. I will be very candid in that I think in very certain applications, what you would probably see is EPN probably maybe outperform right now. And in other applications, LDF outperform EPN. And what I mean by this in terms of long duration test is it depends on the total stress you're putting across the film. I'm sure there's certain regimes where EPN might be better. For the most part, LDF is at least comparable or outstanding with respect to EPN.
All right, and then the follow-up question to that is, you mentioned price and the level of BOPP. Is there any reference?
Yeah, so
Take that.
yeah, I was going to say we haven't released, a public price list for those, but what I can tell you is that from a pricing target, we are looking at BOPP as our baseline for LDF. And obviously pricing varies depending upon thickness and size of real temperature. So we have a very, very comparable price BOPP level. And then we have one that sits above that, which is our 2000 with LDF 1000 is the direct BOPP replacement. Then we have a 2000 that's more of a PEN PET replacement that go into the higher temperature ranges. But what I think you'll see is BOPP is pretty comparable in a pound for pound, kilogram for kilogram price point. And the same is true for PEN, that you'll see LDF 2000 probably be a little bit cheaper than PEN today.
Our next question is, how have you extrapolated such long lifetimes? What are the acceleration factors in terms of temperature and voltage?
Yeah, these are using the simple exponential scaling. So we do perform empirical testing out to 2000 hours. Typically at 20% over voltages from wherever we're rating it at. We do a good number of significantly shorter duration tests and try to build up kind of those exponential decay curves from there. So it's mostly based on empirical fitting using kind of those exponential scaling laws over as much empirical data as you could take at various temperatures and voltages. That's a really good question, Maria.
And then last question, have you tested Algo non-segmented films from Maria?
I'm assuming that's with respect to metallization build. Sorry, I'm actually not familiar with the term segmented in this scenario. Or exactly.
While we wait on her response, we can move on to
Yep.
our next question. When will LDF be in volume production?
So right now we're anticipating LDF being in volume production in early 27.
And then how does moving to 900 volts improve EVs?
That's a good question. I think the easiest thing is fast charging. If you can put more voltage, more current into the system, you're just able to charge much faster. Usually, as people are kind of incorporating these higher voltage systems in, they're also seeing extended range and things like that. And this is just fundamentally because the higher voltage means you can actually handle, or the higher voltage means you require less current. And so you just get lower loss. You can use less cabling. You need less cooling systems like we talked about before. And so just kind of across the board, 900 volts is just kind of leading to a reduction in the extent of components I need across the board. Yeah.
All right, we will end it with this one last question. Can we get samples of LDF?
Yes, we do have samples available, range in thickness from 4 micron. I think, John, what did you say? 12 micron was the top we did this last run?
Yeah.
Yeah.
12 and a half, but yeah.
Yeah, 12 and a half. And what's the continuous length on the sample rolls, John? It's about 2,000 meters.
Yeah, it depends on customer needs, I would say. A lot of people only need 500 meters, and we can do that all day long. If you need longer, generally we do up to 2,000 meters for prototyping purposes.
And the width on those rolls could go to 600 millimeters, if I recall.
Yep, that's correct.
Okay.
All right, that will conclude our Q&A portion for today's webinar, Power Systems and EVs at 900 volts, the next bottleneck. If you have any more questions that were either not answered or that you would like to have answered after the webinar, we will reach out to you directly with those answers, and you can also reach out to our team. Thank you to all of our viewers for joining us today, and thank you both to Sean Walsh and John Tomko for their insights into the power systems. If you are interested in joining us again, please pay attention to your inbox where you will receive the slides and recording from today, collateral around our discussion, and information about our next webinar over motor start caps that will be November the 18th at 12 p.m. Eastern Time. If you have any topics that you would like to see, or if you would like to join us and be a panelist, please reach out to what'snext@peaknano.com. Thank you again for joining us today, and please stay connected through the following platforms. We look to see you again.
Thanks, guys. And Maria, we do see your other question there. We'll email that to you directly.
Oh, yeah, just saw it now. Yeah, we'll send that off. Thank you all.